All right, so here we are with a ski slope problem. We have a skier at the top, and I'm assuming in your notes you'll draw it beautifully. We have a skier at the top who is at rest. Now, he's just barely balanced right there. A gnat lands on his back, which pushes him forward, and therefore he then starts to go down. But his initial speed is so close to zero, that's good enough. As he's going down, we need to do a force diagram because this is not free fall here. So we need to take that into account. And so let's take a look at the force diagram when he's at this spot right here. So if I did the force diagram there, we have two forces acting on him, closer to 3 or 4 in reality, but 2 that we care about. So as we're looking at it, we do have his weight acting down. We have a normal force acting up at an angle perpendicular to the angle of the incline right there. Reason we make it a ski slope problem is I want friction to be equal to 0. And so friction equal to 0. And so there normally would be friction acting back, but there's not enough information to solve it if I gave friction. And we're also ignoring air resistance. That's the other force I was thinking of at the moment. So we now have to go through and think about the work being done. We have work, we have a normal force. Work, conservative, it's on the list. It's the one force that's conservative. So this is conservative. Normal force, it's not on our list of conservative forces, therefore it is non-conservative. It is non-conservative. And so we need to figure out how do we deal with that. Well, fortunately, we are in luck that non-conservative, in this case, remember that work is force times displacement. It is a dot product. Dot products care about parallel. And so because the movement is going to be this way, and the normal force is that way, no matter where he is, he's always moving perpendicular to the normal force. The normal force does no work at all because they are perpendicular to each other as they go. So the work done by the normal force in this case is equal to 0 because the force is perpendicular to the movement. So we are left again with the only thing doing work here is the conservative work. So let's draw it up. And I need the space. Actually, we'll just squeeze it in over here. I know non-conservative work is equal to the change in energy. This is equal to the non-conservative force times the displacement, which is equal to E final minus E initial. That is equal to 0 because of the perpendicular nature of it is equal to this. And so we have E initial equals E final. This is exactly where we were before. We now go through, break it into parts. So kinetic energy plus potential energy initial is equal to kinetic final plus potential energy final. We now do the formulas. Formula for kinetic energy is, I'm hoping that you said correctly, 1/2 mv squared. The formula for potential energy is, I'm hoping you said correctly, which one? The one associated with this conservative force, which is mgh. Initial is equal to 1/2 mv final squared plus mgh final. Similar to what we did before, we now need to establish what is 0. Well, that's equal to 0 because I said the initial speed was close enough to 0 to count. So yeah, you're getting, it's just barely at the top of the frame here. I'm going to adjust the camera slightly, so sorry for those who get easily motion sick here. There we go. And now you can sort of see the top of my head. So because we said the initial speed was 0, initial speed is approximately 0 meters per second. And now we have to establish where's the height equal to 0. Now the two logical places are at the very top or the very bottom. That will eliminate one of these two terms. We could choose in the middle and keep them both, but let's try to save ourselves some math here. So I'm going to make h is equal to 0 at the bottom, which means my final potential energy here is 0. because I said so. And so we now have reduced down to this, which we've seen before. And so mgh initial equals 1/2 mv final squared. The m's cancel out just like before. And so v, the final speed, is equal to the square root of 2gh initial, which is square root of 2 times 9.8 times 50. 50 meters comes from over here. I'm hoping that it is in screen. I have to establish the initial height from the bottom to be 50 meters. And so now, pull out the handy dandy calculator and do 9.8 times 50 times square root. And we have a final speed of 31.305 meters per second. I know it's meters per second because we're finding speed, and we're dealing only with SI units. We only have things in meters. That's meters per second squared, that's meters. And so we'd end up with meters squared per second squared, or meters per second. Now, at this point, I would ask if there are any questions. I'm assuming if you have a question, you might want to email me. So while the person went down, the person had so much fun, the person decided to go back to the top and do it again. In the meantime, there's a cave-in right here. Let's write our friction is still 0. There's a cave-in. And he's not aware that there's this big hole there. Now, don't worry, he's not going to be hurt. At the bottom, there's kittens, cotton balls, and clouds. So he's going to land into something soft. He will not land on any kitten, because as you know, kittens are cute. They should not be harmed. So as it's coming along, he's going to suddenly, and then he's going to land into something soft. The question is, what is his speed at this point? Well, pause if you need to before we go over the answer here. We'll take a breath, give you a chance to pause it if you're going to. All right, so because I'm assuming you've unpaused it or just let it go because you absolutely know what the answer is. The answer is 31.305 meters per second. It does not change. The problem is the same. If we look at it, there's nothing that is different here. He loses the normal force, but the normal force wasn't doing work anyway. So the only force doing any work is the weight, and so that stays the same. So it's still the same. Now, what is different between the two problems is the velocity. The velocity is not the same. The speed is the same, but the direction is not the same, and that is part of the nice thing about energy. We're not dealing with vectors. The bad thing about energy is that we're not dealing with vectors, and we lose some of the directional aspect of it, and we have other mechanisms for that. So, in the meantime, we're about to give you a chance to sort of catch up on your notes, or I'm assuming you're hitting pause when you need to, but I'm about to change the problem again. So the kittens tell him the magic where the door is, so he finds steps, and he goes back up to the top. He's going to do it again because he had so much fun. Except this time, well, he took so much time to getting in there, it snowed again, and this filled in, and so we don't have that gap anymore. All right, so now he's going to go skiing down. Now, also in the interim, while it was snowing, as ski resorts are apt to do, a giant spring was put down here at the bottom. Now, in terms of springs, I do have the prop right here. I have a spring, and it will hang a certain amount in sort of a natural state. If I add a mass to it, this should not be a shock. If I add a mass to it, well, I guess the shock is how much difficulty I have, or perhaps not a shock. So if I add a mass to it, it will now hang down farther. So without the mass, it will hang about here. With the mass, it hangs down there. So with the mass hanging on it, there's a weight pulling down on this mass. There's the spring pulling up on it. If I double the mass, so that is a 20 gram, or if I put on 2.5 times the mass, it should hang 2.5 times longer than it did from the natural state. Again, all of these are compared to where it hangs naturally, not from here, not from here, but from where it was hanging naturally. And it should hang 2.5 times more if this is ideal. And actually, this comes in pretty close to ideal. The indicator to tell you how stiff this thing is or how much force it takes in order to stretch it a certain distance is known as the spring constant. And the symbol we use for it is a lowercase k. It is a lowercase k. I'm doing a slightly fancier lowercase k because k gets used so much. This is known as the spring constant. Now, because the ideal elastic force is conservative, there's got to be a potential energy formula, and so for an ideal spring, the spring force is equal to negative k delta x. This is that the force that the spring exerts is proportional to the displacement, so where it moves from its natural position, and this delta k and the negative sign is indicating that the force is opposite which way it's going. So if I stretch the spring exerts a force upwards. If I compress the spring, it's going to create a force downwards. It's trying to always pushing back towards the equilibrium spot, that natural position. We get into far more detail on this one before the semester's done when we deal with the harmonic motion. Sorry for the blank in there. Now, a sample value for k, if we actually solve for k in terms of magnitude, it's going to be equal to the spring force over the displacement. So I'm just looking at magnitudes right now in terms of units. So the unit of the SI unit for the spring constant is going to be the SI unit for force, which is newtons, over the SI unit for displacement, which is meters. And so a spring constant would typically be newtons per meter. So for this one, let's let k equal 40 newtons per meter. So I'm just going to give that to you. Later on, we'll figure out how do you actually find it. So the question is, when he gets down to the bottom, how much will the spring compress? So if we, again, think about the forces involved. We're going to have three major forces here. We have weight acting on it, conservative. We have normal force, non-conservative, but doesn't do any work. And we have the spring force down here, which is also conservative. So we have only conservative forces doing work. Therefore, I know that energy is equal to kinetic plus potential, which is kinetic plus this gravitational potential plus this spring potential. We have two different potential energy formulas here. We can jump straight to E initial equals E final, or K initial plus U initial equals K final plus U final. And so this becomes 1/2 mv initial squared plus mgh initial plus 1/2, oh, the formula, I didn't tell you that. The formula for a spring, that's the force, the potential for the spring force is 1/2 k delta x squared. So we store just as much energy compressing as we do stretching, and it looks similar in format to the kinetic energy, but that's just coincidence. Also, I do need to give one other piece of information. We do need to know his mass this time. It's not going to cancel out. So mass is equal to, we'll just make it 70 kilograms. The question is, how much will this compress? So I have 1/2 plus 1/2 k delta x initial squared is equal to 1/2 mv final squared plus mgh final plus 1/2 k delta x final squared. And because you can pause and go back, I can erase this. All right, so now we see what we can get rid of. So 1, that's 0 because the initial speed is approximately 0. The spring isn't stretching when he's up there. The spring is just kind of sitting there in its natural position, and so this is 0 because the initial, there's no displacement, it's just sitting there. Let's go ahead and throw units in just to emphasize that's meters per second, and this is meters. Now, we can get rid of two more things. One, the potential energy, gravitational potential energy, the MGH. We have to establish where is H equal to 0. Again, I'm going to pick H is equal to 0 at the bottom. And so therefore this is 0 because I say so. The other thing we can get rid of is, think about it, when you hit the spring, it's going to keep compressing as long as he's moving, and then it's going to stop compressing when he stops moving. And so at greatest compression, he stops moving. In other words, his kinetic energy is 0 because V final equals 0 meters per second. So if you're looking down, you might want to look up. Here's the hand visual one. So it starts out with all this gravitational potential energy, and as he's going down, all that gravitational potential energy gets converted into kinetic potential energy. Then once he's at the bottom, he has all this gravitational potential energy, all this kinetic energy, and then he hits the spring, and all that kinetic energy gets converted into elastic potential energy. So it starts out at gravitational potential, it goes into kinetic, and then that kinetic gets turned into elastic potential. And so finally we are left with, I crossed out the wrong one, sorry about that, equal to 0 because V final equals 0 meters per second. And so we're left with mgh, the initial, is equal to 1/2 k delta x final squared. We're trying to find the amount that was compressed, and so delta x final equals 2 mgh initial over the spring constant and then square root. And so what we're left with is the square root of 2 times his mass, 70, times g, 9.8, times the initial height, 50, over our spring constant, 40. And so now it becomes a calculator exercise. So 2, enter 70 times 9.8 times 50 times 40 divided by square root, and I get 41.4 meters. That's how much the spring compresses. Now, when it gets that full compression there, it will then start to push. It's already pushing him. His acceleration is not 0 when he stops. Its acceleration is at maximum acceleration or magnitude. And he's going to get pushed backwards, assuming we're dealing with frictionless snow. And when he gets pushed backwards, he'll be pushed all the way back up here to the top. Where speed will be close to 0, because the net actually landed on him, giving him a little bit of initial speed that's not 0. He would actually get to the very top, almost stop, and then just slowly fall onto the other side and then plummet to the bottom. And his speed down there would be what we had the first time, the 31, I've erased it, deleted it, the 31 point something meters per second. And that's the ski slope problem. At this point, I'm going to set up for dealing with some friction and a nice little quadratic. Everybody loves a quadratic, and we will be right back.